Now we're in business. All right, before I start talking, I'll entertain any questions from the peanut gallery. I want to get all of your problems done first before I start talking, because you know I won't stop. No problems?
No, I was going to ask you, I know you sent that email about like the private tutoring thing. What was that, what was the other tutoring thing you sent the link for?
That would have been Brain Fuse.
Yeah, or something like that.
Yeah, Brain Fuse is provided free through Blackboard, and you just, has anybody tried to use it?
No.
No?
I want to use it for English.
You use it for English? Okay, good. What do you think of it?
I only use the one where it's like a proofreading of your essay, but not the lectures.
Oh, you don't have like a chat session with someone?
No, I didn't do it yet.
Okay. I think that's an option, isn't it?
Yes, it is.
Okay. So you should be able to get someone to respond to you if you can't find me.
Okay, I have a question.
Uh-huh.
All my methods work. I mean, they're the same thing as I would do the problem. But the thing is, I always get close to the answer, but never the exact answer. Is that because of rounding or something?
Could be rounding.
So instead,
Could be significant figures.
yeah, so instead of doing that, so I just like for the AMU of the element, I just put that instead of rounding it, like the whole thing.
I don't know. This is my first experience with this thing, how that expert system behaves.
Disengage?
Or misbehaves.
Yeah, like my answer would be close, but not the exact thing, but it would be the same thing. So it's round.
Well, if you think there's an error in the system, let me know, and I can contact Cengage and tell them, and they can fix it.
Okay.
Your mine always be a little bit off, but always counted.
Not mine.
Like I could be like a point or two off because I rounded differently, and they always counted it right.
It has about
It
a,
has to be
it has
exact.
about a, I'm trying to think, a 2% error leeway on either side when you do calculations. Yeah, if you're outside that range, then it counts wrong. Timmy, you know about the, let's see, in OWL, there's supposed to be a button down there you can punch and send a message to me. I don't know if any of y'all have used it yet.
I used it among the questions.
Okay, so yeah, just send me those when you encounter a problem like that. Send it to me, and I'll look at it and see if I can deduce where the problem is, either on your side or on their side. Okay.
Thank you.
Like you're getting ready to say something. Okay. Anybody else? Yeah.
We ordered lab coats and they haven't exactly came in yet, but we have like these things that like, they're not exactly lab coats, but they're like for a lab.
How far down do they go?
They're whole body suits.
Yeah.
Like
Whole
arm-
body suits?
Yeah, arms and everything.
We got those. Would that work for today?
Yeah, that's overkill.
I mean, it's definitely.
I have some.
Yeah, we're gonna look like goofballs. It's definitely overkill.
If you want to wear them, fine. But I have some disposable aprons you can wear.
We were like, they just have the-
Yeah. You probably do want to have your legs covered.
Yeah.
Oh, and your arms. Yeah, you may want to wear the suit then.
Okay, that's fine.
Yeah. Nobody has open-toed shoes today? That's good.
Man, it's killing me. I hate shoes. I hate everything about it.
Well, you can wear your sandals right up to the time you go in the lab and then put shoes on.
I dropped it over this morning. So that's like,
Okay. So let's see if we can hit some highlights here. And maybe you'll think of some problems that you can't remember just yet. All right, so chapter 3 is basically on stoichiometry, but in order to do that, we have to get an idea concerning atomic mass units and average atomic weights. You know, how do you calculate those? So, did anybody bother to take a look at the review document?
I haven't got a chance to yet.
Okay,
I was going to
you should. 'Cause it gives you a feel for the type of questions I ask, how I ask them, what they'll look like on test day. Plus, the last few pages are useful information, and these will be duplicated on the exam. So this will tell you what you don't have to memorize.
I got a question about those
Yeah.
papers.
Mm-hmm.
When we're taking the test, are we able to remove like the back papers? Like not rip them out, but just like take them off and instead of flipping back and forth?
Oh, yeah.
Okay.
Yeah, I print them out so that the first of the useful information pages is on the right-hand side. So everything beyond that, you can just rip it off, set it aside. You don't have to be flipping. Yeah. Let me see if I got any extras. Yes, I do. Anybody else? While I'm walking? Okay.
Do you have the power?
Yeah. Pretty sure I do. Here's 4. Here's 3. PowerPoints and the review document are the only things that I've printed out for you, I think. Yeah. Okay. You'll also find in, just a reminder, in Blackboard, that review document in a fillable form. So you can put in your answers and print it off and check yourself. How will you check yourself? Well, you need a key. The key is in Blackboard as well. And one other document, which if you can read my handwriting, I try to be legible, is how I work the problems. So if you try to work a problem in that review document and you just can't figure it out, look, see how I did it. Okay. It's best not to just go in here and see and then put the answer. That doesn't do you much good. The human brain learns by struggling. Okay, so, and the things that you remember the best and the longest are the ones you miss, and then you figure out what the right answer is. Okay, like I remember back in high school, I missed a question on a history test. I think it was, the answer was Blitzkrieg. You know, I never forget it after that. Okay, so let's see. Well, let's just take the first one on the review document. Get us warmed up and going. So copper, naturally occurring copper exists in these 2 isotopes. Okay, and this one. Okay, so first of all, what does that mean? That's the mass number, right? Because it's in that upper left-hand corner. It's reserved for mass number. So the mass number means the sum of protons and neutrons, right? That just means that these are 2 isotopes. Now, we don't need to write, in this case, we don't need to write the number of protons or the atomic number, which would go here, because if we got the symbol, we know what it is. We just have to look at the table, 29, if we needed it. But in this case, we don't need it to do the calculation. The next bit of information we are given is the average atomic mass is molar mass. Well, no, that's not correct. In this case, we're using atomic mass units. 63.55 atomic mass units. So that's a weighted average of these two. The question is, what's the percentage natural abundance of this one? All right. So for this, you need to use a little bit of algebra, because we're not told percentage of either one, right? So what you do is you set up this one, the naturally occurring, as your x. That's your first unknown. And then this one would be what? 1 minus x. Because this, we're going to treat this as a fraction. I know it says percent, but you can't do calculations with percent, because percent is a dimensionless number. It's like parts per hundred. Well, what parts per 100, right? So when you do these calculations, you need to use fractionals. So if this percent, just for instance, was 60% of this one, that number would be 0.6. Okay, and this one would be 0.4. But we don't know that yet. That was just hypothetical. Okay, so how do we arrive at this number? Well, it's a weighted average. In other words, we're going to take this fraction times that contribution, x times 63, plus this fraction times that contribution. So this is 1 minus x times 65. Okay?
Why would you not make them a decimal?
Huh?
Oh, wait, never mind. You're doing the top. Never mind. I see. Never mind. I see.
We could use percent, but we'd have to incorporate a conversion to remove the percent. So we'd have to divide it by 100. So why make it that complicated? But the contribution from this one plus that one is equal to this value. Okay? That's how you get an average atomic mass. By taking the contribution of one isotope plus the contribution from the other isotope. If we had 3, we could do another one, except it would be difficult to make the calculation because we don't know what. This is easy, x and 1 minus x, right? So this one plus that one equals that. So once you get to that point, the rest is easy, right? You have an algebraic expression in one unknown. You can solve it. Yep.
So how do you know if it's going to be 1 minus x? Could it have been 2 minus x? Wait, why is it 1 minus x?
Because 1 is whole. That's the whole amount is 1. If we're dealing with fractions, then the fractional amount of this one plus the fractional amount of that one has to be the whole, which is 1. Okay. So we just have to solve this equation now. So we distribute this one out. 65 minus 65x equals that. And this one. Well, let's be consistent here. 63x. And then put this one over here. Well, that'd make minuses on both sides. What if let's combine the x's first. So plus 63x and minus 65x is what?
Negative 2x.
Negative 2x plus 65 plus 63, 55. Then we want to get positives on both sides. So we just take this one and put it over there. Take this one and put it over here. Okay? this is what? 1.45 equals 2x, and x equals, let's see if I can do this, 0.725, but we probably need to round it. Well, these numbers, since they're like counting pencils, remember that analogy? They are exact numbers. All right, so we got as many significant figures as we want. So this would be 63.00 ad infinitum, and this one also. This one is actually given to you at 2 decimal places. So we can say, okay, we can keep all of those decimals. So x is going to be 0.725 as a fraction, but what percent is that? 72.5%. Okay, well, like that. And this one is going to be the difference, right? If the difference is 1, then that's 2.75, right? Or 0.275. So that means this is 27.5%. But that wasn't the question. This was the answer. 72.5% is that isotope.
So would the answer be 70% on the paper?
Oh, yeah. Right. That brings up another point. If your answer is not in a multiple choice test, if you've got an answer that doesn't exactly match any of these and you don't have none of the above as an option, then you pick the best answer. And the best answer will be 70%. Okay. I probably ought to modify that one to actually put that answer in there. Anybody have any questions about how to do that? Actually working backwards from the way we did it in class. In class, we were given these values and asked, what's that one? Right? So we just multiplied 0.275 times 65 and 0.725 times 63 and add them together and you get that value. And that's what we did here. Only we substituted the value, an unknown, and then solved for the unknown. That's why you need algebra before you take this class. Okay, that was number 1. Let me mark it off so I don't go back and try to do it again. Okay. Number 3 is a trick question. Sort of. It's to see if you really understand what average atomic mass means. The average mass of a carbon atom is 12.011. Assuming you were able to pick up only one carbon unit, that being a carbon atom, the chances that you would randomly get one with a mass of 12.011 is 0. It's a weighted average. 12.011 is a weighted average. There are no atoms with that mass. Okay? Remember when we discussed counting by weighing? We needed an average mass for our units in order to determine. But none of those marbles was the same exact weight as the average mass. Right, same thing for atoms. You will not find a single atom with that mass. That's an average value. So that's why it's a trick question. So, what are the odds of finding a zinc atom with 65.382 grams per mole, or atomic mass units?
0.
0, right? The odds of finding any of these with that mass is 0. Okay, here's a unit conversion. What's the mass of 4 atoms of copper in grams? We're starting out with 4 atoms. That's what you're given of copper. And it wants to know what's that mass? We're headed for grams. So with 4 atoms, what conversion factor do we have that has atoms in it?
Atoms to moles.
Atoms and moles, right? Okay. So we can find out moles. Just need to know what value to put in here.
Moles.
I heard that. Times 10 to the 23rd. Atoms per mole. Okay, so atoms is gone. We're left with moles. Now, can we go from moles to grams for copper? We would need moles down here, wouldn't we? And grams up here to cancel the moles. Whenever you see grams and moles on opposite sides of a divide sign, think molar mass. Grams per mole is molar mass. But as a conversion factor, what is that equal to? 1. So we can flip it if we need to. In this case, we don't need to, because we do need moles on the bottom and grams on the top. So for copper, that value is
63.54.
rounded off 2 decimal places.
60.
63.55.
Oh.
2 decimal places. Here we go. So now moles cancel, and we're left with grams. That's what we want. So now all you have to do is the calculation. And let's see. I always like to check myself, see if there are any errors in my document. So you just say, at this point, you've done all the thinking. Now it's just number crunching. So it's 4 times 1 times 63.55 divided by that number. So I get over here 4.22119 times 10 to the minus 23 grams.
What number did you divide by again?
That one. Right? This one's on top. Right? Anytime you see a number written, a whole number just written, it's in the numerator. So that means this one times that one times that one, divided by this one, divided by that one, divided by that one, is your answer. Okay? Yep.
That's 6.022 times 10 to the 23rd.
Uh-huh. Yep.
I got times 10 to the negative 22 as my answer at the end of it.
What's the coefficient?
Oh, it's 4.22 times 10 to the negative 22.
All right, let me put it back in and be sure I did that right. 55 times, and then 6.022. You're right. My mistake. Nobody else caught that? You did?
Yeah.
Oh, speak up. I'm not infallible. Okay, so now we need to round it to significant figures. If we have restricted the conversion factors, actually, we don't have any, I don't know what to do there. We have no restrictions on significant figures because that's an exact number, it's a conversion factor. This is an exact number as a conversion factor. And that's an exact number because it's a count, 4 atoms. So we can keep as many as we want. So look at the answers. Looks like E is the answer for number 4. So in that one, we just rounded it to there. Okay. I never noticed that before. What do you do when all of your numbers are exact? You're free to choose, right? Okay. Let's see. I'll be sure. Okay. At this point, we have plenty of time. We've done that one, that one, that one. And, these kind of questions throw students for a loop too. Number 6. Number 6 says, you have a sample of zinc and a sample of aluminum. So that was not doing too good. Put up black. We have a sample of zinc and a sample of aluminum. An equal number of atoms of each one. Okay? So it doesn't say how many. So for argument's sake, we can say we have a mole of each. Right? They're equal. Doesn't matter how many there are. Mole's easier to deal with. Which of the following statements concerning the masses of the samples is true? The mass of the zinc sample is more than twice as great as the mass of the aluminum sample. I think what we need is to know how much does a mole weigh, because it's asking us about mass. Right. So zinc is 6538 grams per mole, and aluminum is 2698 grams per mole. So if we have 1 mole of each, we can just compare these numbers directly. So 2698 divided into 6538 is what? 2.4 times. So 6538 divided by 2698 is equal to 2.42. Okay. So the mass of the zinc, since we have the same number of atoms at each one, the mass of the zinc is going to be 2.42 times as much as the mass of the aluminum. We have the same number of atoms, but the zinc atoms weigh more by this much, 2.42 times. So if you have the same number, then the total mass is going to be that much more for zinc than it is for aluminum. Now let's see about question A. The mass of zinc sample is more than twice as great as the mass. Well, yeah, that's true. Now, test-taking technique. You found a right answer. Look at the rest of them and see if there's one in there that says 2 of the above. It doesn't matter if it says none of the above, because you already found one that was right. Right? So look, and I don't see any that says 2 of the above. So A is the answer. Save yourself some time and headache. All right, let's see. I thought that was going to be more complicated than expected. How about, let's just go to 7. This goes another step beyond molar mass of an atom. Now we've got molar mass of a compound. So a sample of ammonia, now we've talked about ammonia, and I think you've seen the formula. But if this type of question shows up on the exam and it doesn't give you a formula, then it's fair to ask me. And I'll tell you what ammonia is. This is ammonia, NH3. Okay? You need to know that to answer this question. That's why it's okay to ask me. The sample has a mass of 43.5 grams. How many molecules are in this sample? Another conversion. If that's the mass, we're headed to molecules. So in order to convert, we need something that will give us that and then this. So 6.022 times 10 to the 23rd molecules per mole. Remember, mole is just a number. You pick the units. If you need molecules per mole, fine. Atoms per mole, fine. Electrons per mole, fine. It's still the same number because a mole is defined as that many objects. But we need to go back here because we haven't got to this point yet. We've got to convert that to that. So what's the magic number here? How much does a mole of this weigh? Nitrogen is 14.01 grams per mole. Hydrogen, 3 times hydrogen, is 3.03, because each one is 1.01, right? But you got 3 of them. So we have 4.04. 17.04 grams per mole is the molar mass of that compound. Okay? To get the molar mass of a compound, all you have to do is add up the molar masses of all of the atoms in the compound. This is only taken once. These are taken 3 times. So you just look over here, round it off 2 places, 1.01 times 3. That's where I got that number. 3 times 1.01. Now we have a value for the molar mass of the compound. There. Now the thinking's all done. The rest is number crunch. I get this one right. Catch me and see if I did it wrong. Is that what you got? Now, we do have to round this one because we only have 3 significant figures here. So we're going to round to this place. That means that's greater than 5, so it has to be 1.54 times 10 to the 24th molecules. Let's see if that was in the answers. Yep, there it is, D. Okay, any questions? The only difference between this one and the one before, actually the one before the before, was instead of atoms, we had to determine molar mass for a molecule. All right, let's see. About 11. Let's just get harder and harder, why don't we? Calculate the molar mass of barium sulfite. So you're given barium sulfite. Okay. Can you find barium on the periodic table? Yep, it's right over here. It's a big fat one. 137.33. That's just for one of them. But how about sulfite? Can you find it on the table? Oh, what is it? Right. Look at your polyatomic list. And that should be, let me just check, that should be included in useful information. Yep, there it is. So it'll be on the test. You look up sulfite and see what it is. So sulfite is SO3 2 minus. Barium is what? 2 plus. So all we need is one of each, right? Barium, sulfite. One of each balances the 2 plus, 2 minus charges. So the correctly written compound is just this and that. So now we've already looked this one up. So barium is going to be that one. Sulfur is going to be what? 3207. Oxygen is 3 times. So rounded off to 2 places is 16. But we need 3 of them. So then just add them up. Okay? 16 is 48, I think. 3 times 16.
Yeah, it's 48.
And then 137.33. 217.40. 217 grams per mole. Probably want to round that off. Well, let's see. This would be 0, and then we add them together. No, that's right. So we've got 2 rules going on there, don't we? Add, subtract, multiply, divide. Multiply, divide comes first, right? And we still have these 2 decimals. So when you add them up, you keep it down to that place. So 217.40 should be on here somewhere. Yep, E for number 11. That's the molar mass for barium sulfite. So the point is here, not only do you have to know how to calculate molar mass, you still have to remember how to write compounds from their names, right?
So, okay, now we have to have 3 to balance out the rest of the equation.
What?
On the, for the equation, the formula, like barium sulfate. So
Sulfite.
sulfite. So there's
2 plus
2 plus.
and SO3 2 minus is the sulfite.
So when we say we have another one like this on our test,
Uh-huh.
we have to write that formula.
Mm-hmm.
We write SO3.
Yep.
If it gives us, okay.
That's the sulfite. And you can find it on your polyatomic table.
All right.
Oh, while we're here, what if I give you barium phosphate?
Won't be,
Okay, barium's the same, right? What's phosphate?
Has a negative 3 charge.
Right, what's the formula?
Um,
D what?
04,
04,
3
3 minus. Okay. How do you balance an odd and an even?
Make the charge to 6. 6 plus and 6 minus.
switch.
Right. Cross multiply. So if we take this one, that one, go 3 down here, parentheses, 2 down there. Because that charge belongs to the whole unit. It's not separated. So 2 of these would give you 6 minus, 3 of those would give you 6 plus, you're balanced. Then to do the molar mass, you'd have to say 3 times that, and then 2 times whatever phosphorus is, 30.97, and then 8 times oxygen. Add them up. So that's a large molar mass, simply because of the way we had to write the compound. Okay? I'd be just sneaky enough to do one like that. Okay? Be forewarned. Okay, let's see what else we've got here, lurking in the shadows. What about this one? Let me see if I've got any. I do have extra credit on this one.
On the test itself.
Yeah, there's a bonus section. The required section, the section upon which your grade is based. You know, when I do the division, 39's on the bottom, and the points you get is on top. But if you get any of the bonuses correct, then I just add those up here, and that stays the same. Okay. That's the beauty of bonuses. You're not divided by any of the bonus numbers. Okay, back to the topic. Where was I? Oh, here we go. Let me see how difficult this one is. Okay. 17, let's try that one. So what do you get? A compound is composed of element X and hydrogen. So X and hydrogen. Oh, okay. There's more. Analysis shows the compound to be 80% X. And we're also given that there are 3 times as many hydrogen atoms as X atoms. So that means 3-to-1 ratio. Remember, this is the simplest whole number ratio, unless you're given exactly how many. So we're saying there are 3 of these for every one of those. That's what that says. What's element X? All right. So this is like, let's say we have done empirical formulas and molecular formula calculations, haven't we? Okay. So when you're given percent, you can't do any calculations with that. You need to know mass. So since we're given percent, let's just assume that we've got 100 grams of this. Okay? So how many grams of X would that be? 80% by weight? Weight. So it'd be 80 grams of X for every 100 grams of sample. So that means X equals 80 grams. So how much hydrogen would that leave us? Hydrogen then is equal to 20 grams. Okay. So we don't know what X is, so we can't calculate how many moles of X there are. But we do know hydrogen, so we can calculate how much of hydrogen there is, right? How many moles of hydrogen are there? So it's grams, moles, right? Grams have to cancel. 1.01. So 20 divided by 1.01 is what? 1.98. Actually, this goes to 3. What did I say? No, not 1.98. 19.8. Okay. So, you guys are just going to sit there and let me make these mistakes. All right.
So where did you find the 20 grams for hydrogen?
Because the compound's only made up of these two, and we have 100 grams of it. And if 80 grams is X, the rest of it has to be hydrogen. Yep.
But where did the number 20 come from?
I just answered it. 80 plus 20 is 100.
Oh.
Oh,
Okay. So since we know it's hydrogen, we can calculate how many moles that is, right? So this is so many moles of hydrogen. How many moles of X do we have? What's the ratio? Moles of hydrogen per moles of X. 3 moles of hydrogen for every 1 X, right? 3 moles of hydrogen for each 1 of X. Just like we were working the stoichiometry problem. So those cancel. And 3 into 19.8 is what? I'll let somebody else.
6.6.
6.6. We got 3. 6.6 what? 7?
It's just rounded off to 6.6.
Oh, you got to set up your calculator to give you more decimals. Okay, it is 0. And that's moles of X. Okay. Based on our calculation, we have 6.6 moles of X, and that many moles of X weighs this amount. When you have that situation where you know how many moles there are and how much it weighs, you have molar mass. So 80.0 grams per 6.6 moles is what? Uh, 12.1 grams per mole. Now, where do we find grams per mole? Just look on here somewhere till you find close. Nothing else is close to it. So with experimental error taken into account, X is carbon. Okay. Yep.
On this question in particular, like just where it was close, it'd be carbon. But
Yep.
So there is a non-do above that.
Oh, none of these?
Yeah.
Yeah, I probably should take that one out and put something else in there. Yeah. When you get that close, yeah, you should say carbon.
Okay.
But if I did something like that, and you said, I did these calculations and it wasn't there, so I put that answer, I say, okay, I'll give you credit. Because you can show me your calculations. Yeah, you actually did them, so you know what you're doing. It's just multiple choice says the answer's not there, right? Okay. Yep.
So when you have to put in a theoretical answer, number, is it a good idea to always do 100, or could have done 10? Doesn't.
It would have worked either way.
Okay.
Yeah. I use 100 because this is 80 parts per 100. So if it's weight, it's 80 grams per 100 grams. So the calculation's easy. If we got 100 grams, 80 of them are X. That's why I use 100. Whenever you have percent as a value. Okay. You can stop me anytime if something clicks back here and says, oh, I need to know that. You can stop me and we'll talk about what you want. Otherwise, I'm off to the races. Let's see if this one would be valuable. How involved is it first? Not too bad. Number 19. I should be writing these things up here. Number 19. So a substance contains 35 grams of nitrogen. All right. 5.05 grams of hydrogen. And 60 grams of oxygen. How many grams of hydrogen are there in a 153 gram sample of this substance? Okay. There are two approaches, the quick way and the slow way. But the slow way is less likely to present error. If we're looking for the mass of hydrogen in a 153 gram sample. Well, first of all, the long way is find out what percentage by weight is hydrogen in this compound. So we would say percent hydrogen is 5.05 grams divided by the total. Right? Times 100. So what percent is hydrogen in the sample? And, 5.05 point. Is that equal to 100? Pretty close. 5.05%. So we could say the amount of hydrogen in that sample is 153 gram sample. And then for every 5.05 grams of hydrogen, that's based on a 100 gram sample. I should have written sample over here. So we can cancel them. Because this is the amount of sample, but this is the ratio of hydrogen to 100 grams of sample. So that one cancels. And we're left with grams of hydrogen. So 100 divided into this times that. So I get 7.73 in that sample. Which one was it? This one. Close enough. 772 is the closest answer here. It's probably a rounding error. Okay. Let's see if we can move to something a little more substantial. that's a tough one. It looks like a bonus candidate there. Let's try one a little simpler first. Okay, how about this? Number 32. Okay, the empirical formula you're given for styrene. You've heard of polystyrene? Okay. You haven't heard of polystyrene? Anybody have any
So
coolers?
like those cups that they have,
Yeah.
styrofoam.
It's an insulator, right? Polystyrene. Styrene is the monomer, the subunit of the polymer. So they say that the empirical formula for styrene is that. So what do we mean by that? The empirical formula is
Carbon.
right, 1 carbon for every hydrogen. That's the simplest whole number ratio. The molecular formula for styrene, though, could be anything times that 1. Right? Remember when we did that, we put an X here? We want to find out what that X is, to find out what the molar mass is of the actual compound. Right? Okay, we're given the empirical formula, so we don't have to calculate that. So the information we need now is the molar mass of styrene. I say molecular weight. 104.1 grams per mole. Now, how do you go from this to that X? Okay. If we know the empirical weight here, and we're given the molecular weight here, then the ratio of those two will give us that number. The empirical weight equals 12.01 plus 1.01, right, 13.02 grams per mole. Okay. So if we ratio these two, because we're saying if I have a mole of this and a mole of that, then a mole of this will weigh that, and a mole of this will weigh that. But if I have X times that, it'll give me this. So X times that gives me this. That's why you can ratio them. 13.02 equals what? I get 7995. And it's okay to round to the nearest whole number, especially when it's that close. 8. So X equals 8. That means the molecular formula for styrene is C8H8.
Because it was a 1-to-1 type ratio.
Mm-hmm. Yeah,
Okay.
right. This is always going to be, this establishes that ratio,
Yeah.
1-to-1 or 8-to-8. We just didn't know what the real numbers were until we did that calculation. Okay. Any questions about that one? We're going to go to the very next one. (33). Okay. Adipic acid. That's a fatty acid. here or there. You've heard of different types of fatty acids, oleic acid, those type. Yeah. Okay. Adipic acid has the composition of carbon at 49.32% by mass, oxygen at 43.84% by mass, and hydrogen at 6.85% mass. And the question is, what's the empirical formula? With this one, we only have to go to the point of finding the empirical formula. We don't have to deal with the molecular formula to answer the question. So here's one where we want to go, we've got to make a mass out of that. We know the ratio by mass. This is parts per 100. Then if we have 100 grams, we have 49.32 grams of carbon, 43.84 grams of oxygen, and 6.85 grams. That's a lousy 5 grams of hydrogen. Now that we have mass, we can find out how many moles of each one we have. And then we can develop a ratio, a simple whole number ratio of atoms to atoms. So here comes Henry Ford again. So we need grams on the bottom to cancel, moles on the top, because that's where we're headed. Okay? So I have a hydrogen. What's the molar mass for hydrogen? Rounded to 2 decimal places.
1.01.
I have an oxygen.
16.
And carbon.
12.01.
1. Okay. So now we just have to do that calculation before we can go to the next step. 49.32. So I get 4.107 mole. And 43.4. 2.74. And 6.85 divided by 1.01. 6.78. Okay. That's a whole number ratio for each of the atoms in that molecule. But it's not the simplest. Did I say whole number? That's the simplest ratio, but not a whole number ratio. So how do we get the whole number ratio?
Add them all together.
No, you got to keep the ratio. And together won't tell you anything. Divide them all through by the smallest one. Remember, in math, if you divide everything through in a number by the same number, you haven't changed anything. The ratios are still the same. This one's easy. 4107 divided by 2.74 is 1.499. Okay, and 6.78, 2.74 divided into it, 2.474. Okay, now we're getting somewhere. These are very close to 0.5, 0.5, half. So that's 1.5 to 1 to 2.5. So if we, how do you make a whole number out of a half? Multiply by 2. Right? So if we multiply each one of these by 2, we should get rid of that half. So 2 times 2.5 is 5. That one's 2, and this one is 3. So the empirical formula is C3O2. Well, actually, I'm going to write it the way convention says we write it. H5O2. Okay? That's the simplest whole number ratio for adipic acid. This is the empirical formula. We could use that to get the molecular formula, but we would need to know the molar mass of the compound itself by some other independent method. Right? Our first lab in CHEM101 was doing something like that. We found the molar mass of a compound by using colligative properties. Big word, you'll learn it later. Unless you want to look it up, you know, if you're ambitious enough. Yes,
Okay, because I'm trying to do the calculation.
add one back. You want to let him go? Sure. Okay.
Yeah, let him go. You first.
You're still thinking? Go ahead.
So the reason why you times by half, because it was a fraction earlier, is that why? Or you times by 2?
Yeah. Mm-hmm. If you multiply 1.5 times 2, you get 3. We're looking for whole numbers. Got to get rid of that fraction.
Okay, and the 100 grams, that's the reason why, because 49, 43, and 6 are all in 100. Is that why? Or
Oh, if you add all these up, you should get 100.
that's how you got 100.
Mhm.
Okay, thank you.
Yeah. I got 100 because percent means parts per 100 parts. 49 parts per 100 parts. 49 parts per 100 parts. Okay, next.
Okay, so I'm trying to do the calculations on my calculator from basically from this side before we got 32 to 5. But how did you get 4.107? Like which?
I divided this by that. This is in the numerator, this is in the denominator.
All right, so you just write 49.32.
Divided by 12.01.
Okay.
Yeah.
Thank you.
On you guys' calculator, you would say 49.32 and then the operator, divide, and then the number, and say equal or enter, whichever case may be.
Okay, no, thank you. Okay.
All right, so that's 33. Now, let's see, I don't want to get too far behind. Let's move along here. Let's balance some equations. Anybody have trouble balancing equations? How about 40? Okay, we're given this as an unbalanced equation. And you don't have to name all of these compounds. This one might be difficult to name. We're only interested in balancing. And there's our ammonia again. Okay. So, first thing you do is an inventory. What are you starting with? This one's got nitrogen all over the place, so it might give us some trouble. But you don't have any groups of atoms that appear on both sides, right? So you're going to have to do individual element inventory. Sodium, nitrogen, hydrogen, sodium again, nitrogen again, oxygen. So that covers everything. Okay, sodium on this side, you have 2 of them. Nitrogen, you have 2. Hydrogen, you have 2. Oxygen, you have 3. Sodium on this side, we have 2. Nitrogen, we have 1. hydrogen, we have 3, 6. And oxygen, we have 1.
How do we have one nitrogen?
Did I write it wrong?
Formula is in the third house.
I wrote it wrong, didn't I? Sodium, yeah, I wrote it wrong, sorry. Okay, so that means we have 4 nitrogen, don't we? Did I get the rest of it okay?
Yeah, okay.
Okay. Now we want to start, we want to see,
Who's hydrogen?
Yeah, it should only be 4 hydrogen now, right?
say again?
Only 4
Should only be
hydrogen.
4 hydrogen now.
On the right
side.
side. Pre-changed it.
Oh, okay. Now can we go?
Should be.
Okay. Because if you don't get this right, it's never going to balance. All right. Sodium's okay for now. Is there anything that we need to leave till the end? Not that I can see. Because we don't have any standalone elements. So what we're going to have to do is just go backwards and forwards until we get it done. How about we just come down the line and say nitrogen. So we got 4 nitrogens over there. If we have 4 nitrogens over here, how do we get those nitrogens? Well, we could say 4 here, or we could say 2 and 2. That's going to be a problem. So I suggest we go to oxygen. 3 oxygens here, 3 oxygens here, which means 4 sodiums, and still have 3 nitrogens, 4 nitrogens, but we have 3 oxygens now. Oh, that's what we did before. 3 hydrogens, right? 3 plus 3 is 6 hydrogens, right? Okay? 3 hydrogens, 3 hydrogens, 6 hydrogens. So we can check ourselves. See, 1, 4, 7, 10, 13, 14, 17, 9, 13, 17. Right, so we got the totals right. So that gives us so many hydrogens over here, 6 hydrogens. So if we go over here, we want 6 hydrogens, which means 3 times this one, right? 2 times 3 is 6.
Let's go make it, let's see, 4 sodiums.
4 sodiums, And 3 nitrogens plus 1 is 4 nitrogens, is it?
Oh, we're good.
We got it. So if you had started, well, doing what I did and looking at, if we start with nitrogens, we've got 2 places for them, so you don't know what the ratio is. So you're kind of forced to go to the one where you only change 1, and that had to be oxygen. And you might not know that unless you do a bunch of them and go down these rabbit holes, several of these dead-end holes, before you decide that you need to start someplace else. Oh, what was the question? 40? What's the sum of the coefficients? So we take 3. What's the coefficient here? 1. Don't forget that one. We don't write 1, but there's a 1 there. 3 plus 1 is 4. 5 plus 3 is 8. Plus 1 is 9. So that should be E. Okay? Don't forget those ones. Okay, let's see. What about 45? I'm not going to draw the picture up there. We're just going to talk about it. A chemical reaction has an equation 2A plus B yields C. I'll write that part up here. 2A plus B equals C. So the ratio is 2 moles of A plus 1 mole of B yields 1 mole of C. It doesn't tell us that it's stoichiometric, so it's possible to have some of these left over when you get to C, but not necessarily. Okay. Well, let's just take them in order. What do we have in A? We got 1, 2, 3, 4, 5, 6, 7, 8. Yeah. For Roman numeral 1, we have 8 A's. We have 1, 2, 3, 4 B's. So that's the right ratio. Oh, the question is, what's the stoichiometric ratio, right? Okay. That is a stoichiometric ratio for A and B. How about 2? It only has A's and B's in it, right? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Can't be, because the ratio is 2 to 1. How about Roman numeral 3? Okay, A's, 1, 2, 3, 4. And B's, 1, 2, 3, 4, 5, 6, 7, 8. Wrong ratio. Instead of 2 to 1, it's 1 to 2. And then Roman numeral 4. What is Roman numeral 4? Okay, Roman numeral 4 has 1,
C's.
yeah, 1, 2, 3, 4 A's and 2, 3, 4, 5, 6, 7, 8 B's. Right? We don't even have to count the C's because this ratio is wrong. But let's just hypothetical. If this ratio were 4 to 8 and you had 4 C's, could that be right?
Yes.
Nope. Because if it's stoichiometric, all of these have to be used up to give you that many C's. So it can only have C's. You can't have them both there at the same time at those ratios. Okay, because if it's stoichiometric, all of these are used up to give that one. That would be a really tricky question.
So it'd be like on A, not.
Just A, yes.
Yeah.
A is the only one. And what we're saying with A is the reaction has not started yet because you have those ratios. If you have any C's in there, then the reaction has progressed. Okay. So let's keep moving here. Okay. Start simple. 46. Let me see, what are we missing? We haven't even got to chapter 4 yet, have we? All right, we're going to have to kick it up into high gear. 7.11 grams. Potassium chlorate. was decomposed by the following equation. So this equation is balanced. KClO3 is potassium chlorate to give you 2 KCl potassium chloride plus 3 oxygens. How many moles of oxygen are formed? Well, we're starting off with this many grams of potassium chlorate. So how do you get from here to there? The direct route, right? You got to convert it to moles, right? There's a great wall here. Can't cross it unless you're a mole. So you have to go this way, right? If you're a mole. So we got to convert that to moles. So what's the molar mass of KClO3? Well, K is 39.10 rounded off grams. Chlorine is 3545. 3 times oxygen, 16. Right? So now we need to find out what is the molar mass of potassium chlorate. And 48.
Would you not times those by 2 at all?
Nope. The only time you use the coefficient is when you're converting from this one to that one, right? At this point, this speaks to only that formula. That's a common mistake, and I'm glad you brought that out. That's 0.55 grams per mole. So we can convert this one to moles. Grams has to be on the bottom, moles on the top. So we put the grams on the bottom, moles on the top. That cancels grams and gives us moles. So 7.11. I get 5.802 times 10 to the minus 2. And I'm hanging on to extra digits here just to reduce the risk of rounding error. Okay, so this is moles of KClO3. And let me go back. What was the question again? How many moles of oxygen? So the question is moles. And so now all we have to do is convert this moles to that moles. That's where your coefficients come in. So for every 2 moles of this one, we have 3 moles of this one. Okay? So 3 times that divided by 2. And I get 8.70 times 10 to the minus 2 moles of oxygen. Let's see, is that one of our answers? All right, it's given in standard notation. So with minus 2 here, we move it 2 places to the left, right? Negative goes left, positive goes right. When you're going from scientific to standard. Then we look for that one. 0.087 D. Okay? Intuitively, we should recognize that with a minus number here, you can't go to the right. If you go to the right, you make the number bigger. We got to make it small. So you got to go to the left. It's just a check on yourself. Question?
Got a question. Okay. See where we have O3 over here on the left side. On the right side.
3 oxygens?
Yeah, on the right side.
Or here? Or there?
Left side. But
Oh, here.
Yeah.
Mm-hmm.
but if we add 3 oxygens, but it's already got 2, wouldn't that make it like 5 oxygens?
How many oxygens are on this side?
3.
No, 6.
6. Oh, no.
You gotta have the same number of atoms of each element on this side as you do on that
So
side.
if we have like a 2, like a big 2 over on this side,
Uh-huh.
that kind of like times everything.
Propagates through the formula, yes. When you're balancing the equation.
Okay.
When you're actually doing the molar calculations, you only deal with the compound itself. Then you use these for conversions. Question? Let's see if we can get through. How about 64? That was coincidence. I didn't plan it. 46 to 64. I think I'm dyslexic. Okay. 64. For the reaction, and it's balanced for you already, N2 plus 2H2, and I might as well put these N2. They're both gases, yields N2H4. The percent yield for this reaction is 82%. So what does that mean?
The arrow is 80% full. So combined of N2 to H2 is 82%.
Now this is efficiency. The percent yield is, if you're expecting, if the stoichiometry says you're supposed to get 100 grams here, you will actually only get 82. Okay? So this means the actual product mass divided by the theoretical mass times 100. Okay, that's what that means. I ran off the board there. Okay, more information. What's the actual mass of hydrogen produced when 25.57 grams of nitrogen? Reacts with 4.45 grams. Oops, I'm backwards. 25.57 grams reacts with 4.45 grams of hydrogen. What's the actual yield? Okay. It's already balanced, and we can check it. 2 nitrogens, 2 nitrogens, 4 hydrogens, 4 hydrogens. When you have reactants given exact amounts that are being added together, you can assume that one of them is limiting. They're rarely stoichiometric when we do that. So, how do we find out which one's limiting? Well, you can't go over there until you make moles, so you might as well turn them into moles anyway. Right? So let's turn this one into moles. So this would be, I'm just going to put it down here. Nitrogen, 2 times nitrogen is 28.02 grams per mole. And I get that. 14.01 times 2. Okay? So that, oops, can't do that, can I? I need to know moles. right? Now they cancel. Might as well do the calculations on here. 25.57, 8.02, and that's 0.9126 moles of nitrogen. Okay, hydrogen. So I need grams on the bottom here, moles on the top. For hydrogen, it's 2 times 1.01, right? So we divide that into 4.45. And I get 2.203 moles of hydrogen. Okay, that's how much we start with. So how do you tell which one's limiting? You say, all right, if I use all of this up, doesn't matter what that is. If I convert all of this into that, how much is it? So now we go to coefficients. They're 1 to 1, right? So we're going to get this much mole of N2H4 because they're 1 to 1. If all of this is converted. What if all of this is converted? Well, that's 1, and this is 2. So we divide it by 2. 1.101 moles of N2H4. Okay, now we can decide which one's limiting. Which one makes the least amount? Because that one's going to run out first. This one. This is the least amount of N2H4 that can be produced. So this is the one we convert back to grams. Not that one. That's too much. The least amount is the limiting one. We're going to have some of this left over. All right, so we take that many moles and convert it to grams. We need the molar mass of N2H4. Okay, so we have 2 times 14.01 and 4 times 1.01. Let's see, 2802 and 4.04. Oops, hit the wrong button. Let's try it again. $32.06 grams per mole. So 32.06 gives us what? Times 0.916. 2.93. No, 29.3. 29.3 grams of N2H4. What value is that? Actual or theoretical? Ask yourself how we got to that point. We used everything up to get to that point. Have we taken into account yield yet?
No.
Nope, not yet. This is theoretical. It's based on the stoichiometry of the equation. So now we apply the yield. So we have, this is theoretical. So for every 100 grams of theoretical, we get 82 grams of actual. So basically it's 0.82 times 29.3. Uh, 24.0 rounded off. That's the actual amount. Let's see, is that in here? 64. 24. There it is, B. Okay. Did I lose anybody? Questions?
So
Yeah.
why is 8 a whole number if it's 82%?
Because percent means parts per hundred.
Oh, it's over 100 fraction.
Parts per hundred. I just did that instead of doing an additional calculation to correct. All right. Let's see, can we get out of chapter 3 yet? We should, because I'm running out of time. Oh. Before we leave, let's do another pictogram. Let's think ancient Egyptian. I don't think the ancient Egyptians did chemistry. You? Their chemistry was more like voodoo. They had a class of people who knew how to do certain things, like smelt copper and make bronze. But they didn't know why it worked. They just knew it worked. And they passed it down from one person to the next. It was a guarded secret. Okay, so 73. If we have, I'll just draw the first one. These are atoms. And then each one has this one attached to it. Okay, 1, 2, 3, 4, 5, 6, 7, 6. Okay, what's the empirical formula for that compound? If these are individual atoms in a ring and then hydrogens on each one of the carbons.
C6H.
Okay, that would be, this is the molecule. So C6H6 is the molecular formula. What's the empirical formula? CH. You can divide that through by 6 and still get the same, get a whole number ratio. So that's the empirical formula for this one. What about B? This is A. I'm not going to draw the rest of them. So what's the molecular formula for B? C2H4. So the empirical formula would be, right. C, that's going to take some counting. It's got carbon, hydrogen, and looks like oxygen in there. So carbon, hydrogen, oxygen. How many carbons? 1, 2, 3, 4, 5, 6, is it? 2, 4, 6. I count 6 carbons. Hydrogens. 1, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And oxygens? 4. 6. Okay. Now, what's the simplest ratio for these? There you go. That's probably glucose. Okay, last one. We have carbon, hydrogen, and oxygen again. So how many carbons? 6. Hydrogens? I count 10. Do you count 10?
Yeah.
And the oxygens? 2. Okay. So what can we divide through here? I'd pick the smallest one.
2.
Divide through by 2, yeah. So that makes that one 1. Wait, no, right, 1. 5. And 3. C3H50. So those would be the empirical formulas for each one of those. Let's see, that would take too much time. Let's get on to chapter 4. Okay, we got 40 minutes. I don't want to eat into your lab time. All right, let's go for 1. And this is chapter 4. An unknown substance dissolves readily in water, but not in benzene. And it tells you benzene is a nonpolar solvent. So you've got water as a polar solvent, benzene's a nonpolar solvent, and it dissolves readily in water. So what does that tell you about the compound? Probably polar, right? Like dissolves like. Polar dissolves polar, nonpolar dissolves nonpolar. And if you put a nonpolar in a polar, it's like vinegar and oil in your salad. It separates. They don't like each other. It's called hydrophobic. Okay, more of the question. Molecules of what type are present in the substance? Oh, I just told you. Polar, right? So that's B. Polar. Okay. All right. This is a test of memory. And 2, when you put a solute molecule into water, and it tells you it's a salt, and it tends to fall apart. So remember the example that we were given. Sodium chloride. Okay. It's a network. So these are pluses, these are minuses. So what does water do when it comes in? Well, if it finds a sodium, it would have to approach as this, because this side is negative, right? And it would tend to pull because these guys over here are still associated with other water molecules, and they're pulling and say, no, you can't have that sodium. It's pulling on them. So it says, yeah, I win. So it keeps pulling, and eventually that sodium comes out. So when that sodium comes out free in water, what happens? A bunch of other water molecules surround it. As far as sterically possible, that is, as far as there's room for everybody to get in there, they form bonds with that sodium. Okay? And that name is called what? Works similarly for chlorine, but we're going to talk about sodium right now.
Would be coagulation.
Coagulation? Sorry.
Hydration.
Hydration. Right. Because the prefix hydra means water. So that the ions from that salt are being hydrated. All right, let's see. How about number 4? All the following are weak acids except. You just have to find the strong acid. Okay, you have to remember what are your strong acids, right? Anything made from a halogen, except for this one, is a strong acid. Okay, those are strong acids. By the way, what do we mean by strong acid or strong base?
Anything above 7, below 7.
Now, the definition is, if that compound completely dissociates in water to make the protons plus the anion, it's a strong acid. The temptation is to say, ooh, that's a strong acid, I better not put my hand in there. Not chemically definition, the chemical definition is just complete dissociation. So it would do this, and make that. Now, if the concentration is very high for a strong acid, yeah, you want to keep your hand out of it. But it can still be a strong acid at low concentration, right? Stomach acid is between 10 to the minus 1 or 10 to the minus 2 and 10 to the minus 1 molar. Okay? So it's between pH 1 and 2. You could probably put your hand in stomach acid for a short period of time, right? If you had any cuts on it, you'd find them in a hurry, right? But you wouldn't want to leave it in there very long. But the strong acid here is that one. Okay,
Is that hydrochloric?
hydrochloric, yes. Hydrochloric, hydrobromic, hydriodic acids. There are other strong acids, what? Polyatomics, nitric acid, sulfuric acid,
Phosphoric acid?
I don't think phosphoric is strong. No. It can be dangerous if it's high concentration, but it's not by our definition a strong acid. Okay, so out of that list, which one fits?
Hydrochloric.
Is hydrochloric in there?
Oh, never mind.
Its neighbor is hydrobromic. That's the only strong acid in that group.
Well, you said anything that is combined with halogen, well, fluorine's in there.
No, I said leave that one out.
Oh.
It's a special case. Hydrofluoric acid is weak. By our definition, it's still dangerous. Concentrated hydrofluoric acid is probably more dangerous than any one of those because of the reaction that it undergoes when it gets in your skin and in your bones. If you drop strong, concentrated hydrofluoric acid on your skin, it'll go through and out the other side because of the way it reacts with your skin and your bones. So we were always very careful when we used it. Doubly careful, double gloves, protection under the fume hood. Pull the sash down and just reach what you had to. Okay, those are strong acids. While we're on the subject, what about strong bases? How do you get a strong base? Hydroxides of any one of those. So lithium hydroxide, sodium, potassium, rubidium for that matter. Oops, that's not right. Or magnesium hydroxide, right? That's a polyatomic -1, 2 plus, so you need 2 of them.
Does cesium not count?
Yeah, it would work. And beryllium for that matter. Calcium. And strontium, barium. Okay, here's a caveat. These guys completely dissociate water. These guys also. And they might become less soluble down here. But the problem with these is they're strong bases, yes, because whatever goes into solution completely dissociates. But they're only slightly soluble. So only part of them go into solution. Okay? So whatever goes into solution makes this plus this. But since it's only slightly soluble, you don't get much of it in solution. But still, by our definition, it's a strong base. Okay. Let's try. About 12. How many grams of sodium chloride are contained in 350 milliliters of 0.287 molar sodium chloride? What's the mass of sodium chloride contained in that solution? Can we go there directly by a single calculation? Nope. Concentration is what? Moles per liter. So we can find out how many moles there are, then we can find out how many grams there are. So if that's moles per liter, and the definition of molarity is mass per volume, we're looking for, moles per volume. Correct abbreviations. We want to find out how many moles there are. So N equals molarity times volume. Molarity is 0.287. And then in order to cancel this moles per liter, we need liters over here, right? So how many liters is 350 milliliters? A 1,000 milliliters in a liter, right? 0.350 liters. Move it 3 places to the left. 1, 2, 3. That gives you liters. If you've got liters and you want to go milliliters, just move it 3 places to the right. Because that's tens, hundreds, thousands. Okay. So now 0.35 times 0.287 is 0.1005 moles of sodium chloride. So now we can convert moles to grams. We just need the molar mass of sodium chloride. Right, so you look for sodium, 23, round it off, and chlorine, so that's 5845. There we go. So it's going to be in the neighborhood of 5.8 grams. Let's see if we're in a hurry on a test. 5.87, there you go. Let's do it anyway. 58.45. 5.87. You have to do the calculation to get that exact number. So that's how many grams are in this many milliliters of that concentration. Okay? Questions? Let's turn this thing inside out. Maybe it'll erase better. Let's see, that was 12. How about $18? This is on page 21. I should have numbered them consecutively, right, from beginning to end. But I must have done chapter 3 independently from chapter 4 at one point.
And you put it together later on.
Yeah, put them together later on. Yeah. Okay, for this one, what volume of 18 molar sulfuric acid okay, aqueous, of course. That is very concentrated, 18 molar. It's not the most concentrated. I think 98% is 36 molar, something like that. So that's, don't stick your hand in, okay? This is the kind of stuff they use to pickle steel. Okay, so it's very reactive, and that's why around the steel mill you'll smell sulfur.
Yeah, you can use it to remove rust and corrosion and stuff off of it. I've done it before.
Yep. It's probably safer to use phosphoric acid though. You can. They used to have this stuff you could paint on your steel fence when it rusts, and it would convert the iron oxide to iron phosphate. Then you can just paint right over it. I think it was kind of a green color,
Yeah.
kind of a gel. You just stick your brush in there and slap it on. Fairly safe because phosphoric acid is a weak acid. Okay, so you got 18 molar. What volume of this one? We want to know volume of that one is needed to prepare 2.3 liters of 0.145 molar H2SO4. Okay. So you remember the formula that works for this one? Okay, molarity times volume before equals molarity times volume after. So you just have to figure out which one is which and make sure you got them designated here.
Well, where is 18 in it?
So, right, V1 is this one. I mean, excuse me. Oh, yeah, V1 is that one. But this one is also M1. This would be the concentrated side. So this would be 18 molar times whatever volume equals this molarity, which is M2, and this is V2. So this would be 0.145, and this would be 2.3 liters. Now, let's look at the question for a second. The answer is in milliliters, right? And remember what I said about these ratios? If you got a ratio of molarity and volume, you don't have to use liters here because the liters are going to cancel. Right? You can use milliliters. So 2.30 liters is 2,300 milliliters. So if we use milliliters instead, our answer is going to come out in milliliters, right? Because V1 equals 0.145 molar times 2,300 milliliters divided by 18 molar. And then the volume of the more concentrated one that we need to be diluted to this final volume is whatever that calculation is. We've done all our brain work, now we just need to do calculations. So I got 18.5 milliliters. Let's see. And round it off, 19 milliliters. Probably rounded it off because of this. Okay, so that's how you make a diluted solution from a concentrated one. Okay, we have 20 minutes. Let's see, I want to be sure I cover all the topics. Can you recognize types of reactions? About 26. The following reactions are examples of blah. Okay, given these three reactions, okay. This one, cerium. I don't think I had you memorize that one, did I? Cerium, where is it? Here it is. Yeah, you didn't have to memorize that one. Okay, and this one. We've never written it that way before, so I'll have to tell you what it is. So, this is acetate polyatomic ion that makes this acetic acid. It's an abbreviation. Okay, what kind of reactions do we have? Well, let's see. Well, and of course, this is a multiple choice, so you got to pick from what's here, right? Yeah, that's a synthesis, but there's no synthesis there in the choices. So we look for something else. So I would look, if you've got a cation here and an anion there, I'd look at my solubility table, right? Remember the one with grayed out squares? It'll be on the test too. Right there, last page. So if you look at this one and follow it down till it meets this one, you'll find that this one is solid. So this reaction is precipitation. And in fact, it's a net ionic equation. So this one would be paired with some anion to get it in solution. This one would be paired with some cation to get it in solution. For instance, that might be lead 2 nitrate in solution. And this might be potassium iodide in solution. But the only reaction we're interested in is that cation and that anion. Because the nitrate and the potassium are both soluble together. So they don't react. They're spectators. How about this one? This one, I would look at the charges and the oxidation states. This one goes from 4+ to 3+. What has happened? Right. That's good. Gain. Gain 1 electron per cerium. Right? If you go from 4+ to 3+, it had to gain 1 electron to cancel out one of the positives. So that means this one went from -1 to 0. So it would, there would be a loss of 1 electron per iodide. So this is a redox reaction. Right? Anytime you have transfer of electrons, you have a redox. Okay, so what about this one? Well, you've got an acid. Do you have a base? Is ammonia a base? Yeah. Acid, base. Reaction. What we've left out here is the water. But it's still an acid base. You have an acid base. This acid produces a conjugate base. I defined that, didn't I? Acid base? I hope so. Acid, when it loses a proton, becomes a conjugate base because a base is a proton acceptor. So without the proton, it's willing to accept that proton back. So now it becomes the conjugate base of that acid. And this becomes the base which gained a proton, right? It's a proton acceptor. Now it has this extra proton, which makes it a conjugate acid. That was a tough one. Let's see. So I would take a look at those types of reactions. See if they make sense to you. Let's see. I want to get through before we if we can do this one, 65. Four. 65. Let's try it. So when you're balancing a redox reaction, your focus is on electrons. The unbalanced version is this one. I'm leaving out the states. They take up too much room. Okay, so let's look at, there's iron at 2 plus and 3 plus. So what happened to iron? It lost an electron, right? Lost 1 electron per iron. How about hydrogen? H plus, that's H plus by the rules. That's 2 minus by the rules. This is still 2 minus by the rules. So oxygen and hydrogen don't enter into the redox part. The manganese might. That manganese is 2 plus, what's this one? 4 times 2 minus is what? 8 minus, right? But we got to hold one of them out for that charge. So that means we only have to balance 6 minuses. That means this one has to be 7 plus. And check yourself. 7 plus, 8 minus, gives 1 minus. So manganese went from 7 plus to 2 plus. That means it gained 5 electrons per manganese. So we need to balance the electrons. So how would we do that? Well, we need 5 of these, don't we? If we do 5 of those, that makes 5 of those, that makes 5 electrons lost, and 5 electrons gained. So the electrons are balanced now. Oh, what's the question? What is the ratio of Fe2 plus to MnO4? Okay, so we got the answer we need. The ratio of this one to this one is 5 to 1. We don't even have to finish balancing it to answer the question. I thought it was going to be more complicated than that. We're not even going to balance the whole equation. Let's see. How about oxidation states? Everybody good with oxidation states? How do you figure oxidations? We did some here. Let's say, what if we have, let me take a booger, see if I can find a bad one. How about 2 nonmetals? Okay, nonmetals together means that they're not ionized, right? That's only when you have a metal and a nonmetal. So we have to think of it in terms of oxidation states. It's kind of a pseudo charge. So we have something like this. Then we go back to our rules. Oxygen's always 2 minus, unless it's a peroxide, right? But in this case, it's 2 minus. So we have a total of 4 minus oxidation state. Only 1 nitrogen, so that 1 nitrogen has to balance all of those minus charges. So the oxidation state for nitrogen is 4 plus. Let's see, balancing equations. We did one of those already. Let's see if we got anything else in here that could spin us for a loop. Question?
So if you had O3 with a, would it be 6 plus?
That's not a valid molecule. That is a valid molecule, a polyatomic ion. So in that case, oxygen is still 2 minus, times 3 is 6 minus, right? Okay, but the 6 minus needs to be balanced only to the point that it leaves a negative extra. So you only have to balance 5 of those negatives and leave 1 out for this. All right, so that means this one is 5 plus to balance that one.
And the reason why you didn't do that for the NO2 is because of non-metal and metal?
No, they're both nonmetals. The only reason I didn't do it for this one is because there's no charge. Say, NO2 is an uncharged molecular species, whereas this one is a polyatomic. Okay, so whenever you have that charge out there, you got to be sure and balance only enough charges to leave that extra charge out there. Like this one, right? So each hydrogen is plus 1. So you have 4 pluses total, but you need to leave 1 for that. So you only have to balance that 1. So that means this one has to be 3 minus. Nitrogen has lots of potential oxidation states. And that's why when you look at the periodic table, not this one, but maybe the one that's given in, yeah, the one that's given in your useful information, you see a lot of charges there. Those are not necessarily charges. We started off learning them as charges, plus 1, plus 2. Minus 1, minus 2. But eventually, you need to start thinking of them in terms of oxidation state. Now, for a charged ion, the charge is the oxidation state. But for something that's not charged, you can still, for bookkeeping purposes, think of it as a charge, but back here say it's not really a charge. That's why we gave it a different name, oxidation state. Yes?
Okay. So for like NH4, and H has a charge of 1,
Yes.
and where it's 4 it'd be 4. But where did you get 3?
I took that plus away from this one.
Oh, okay.
So I would only have to balance this one. I want to be sure and leave 1 out for there. So then I just reduced it by 1 to hold that one in reserve and then balance those 3.
Okay.
And you can check yourself, say, all right, 4 times plus 1 is plus 4, right? Add that together with 3 minus, that equals a plus 1. And that has to be equal to the charge on the species. If it's neutral, they have to come out to 0. But if there's a charge, you gotta come out to. For instance, chlorate, right? 2 minus for the oxygen, 6 minus total, but we're going to hold one of those out. So we only have to balance 5 minus. So this one is 5 plus for chlorine. Okay. That's chlorate. What if we go to chloride? So that's 2 minus, 4 minus, 3 minus, because we're going to hold 1 out. That means this is 3 plus. So the oxidation states of chlorine in that family of polyatomics change each time you take away an oxygen or add an oxygen. That's why this one, perchlorate, +7, has extremely high oxidation state. That's why perchloric acid is such an effective oxidizer and why we used it to destroy organic matter in our plant samples. Okay, we're out of time, I think. We need to go in the lab and do our thing. I've already started the water heating, so it should be very close to boiling, if not at. Lab's open. Guess I need to show you where your aprons are. I'll come back and get this stuff later. Let me get you rolling in there. I'll turn this off so it can be compiling.